Hi, this is Ruben Polianza, your personal tutor. So you want to know all about the special theory of relativity by Albert Einstein? Great! You've come to the right place. So first, let's discuss the special theory of relativity, time dilation. So what is time dilation, by the way? So let's give its definition. Time dilation, by definition according to Wikipedia, in physics and relativity, time dilation is the difference in the elapsed time as measured by the two clocks. It is either due to a relative velocity between them or either to a difference in a gravitational potential between their locations. When unspecified, time dilation usually refers to the effect due to the velocity. So let's explain this in a simpler way. I'm gonna give you some example. The important thing that we need to accept is that the speed of light is the same for all observers. So let's imagine a beam of light being reflected between two mirrors. Let's replicate this setup so we have another beam of light being reflected between another set of mirrors. But this time, the mirrors are moving close to the speed of light. We can see in the moving set of mirrors that this beam of light is moving a greater distance. Now, let's put a couple of people in this scenario. Meet Ben. He sits inside the moving set of mirrors and then sits inside the stationary set of mirrors. The speed of light must be the same for both Ben and Ten, and their light beams must hit the bottom mirror after the same amount of time has passed. But as Ben's light beam is covering a longer distance, how is that possible? Well, the only way for that to work is if time for Ben slowed down. Time for Ben has slowed down, which allows his light beam to travel a greater distance. Always remember this formula. Speed is equals to distance over time. As Ben's distance is more, the value of his time must be more. Time has slowed down for Ben. This is called time dilation. This is quite intriguing and hard to grasp because it seems to go against what we experience on a practical level. But to understand the theory of relativity, you must stop thinking of time as a fixed unit for everyone. Time is relative. Let's go to special theory of relativity, length contraction. So what is length contraction? So by definition, it goes this way. According to Wikipedia, it is the phenomenon that a moving object's length is measured to be shorter than its proper length, which is the length as measured in the object's own rest frame. In the previous one, we spoke about how the speed of light remains the same for Ben and Ten, because while the distance Ben's light beam travels is more, his time has dilated. However, distance and time don't increase by the exact same amount. In fact, time doesn't actually dilate enough to account for the speed to remaining the same for both boys. Something else happens, length contraction. When objects are moving close to the speed of light, not only does time slow down, but the object itself contracts. This is called length contraction. So let's go now to inertial frame of reference. So what is inertial frame of reference? By definition, according to Wikipedia, in classical physics and special relativity, an inertial frame of reference is a frame of reference that is not undergoing acceleration in an inertial frame of reference. A physical object with a zero net force acting on it moves with a constant velocity, or equivalently. It is a frame of reference in which Newton's first law of motion holds. An inertial frame of reference can be defined in analytical terms as a frame of reference that describes time and space homogeneously, isotropically, and in a time-independent manner. Conceptually, the physics of a system in an inertial frame have no causes external to the system. An inertial frame of reference may also be called an inertial frame of reference, inertial frame, Galilean reference frame, or inertial space. So we often discuss motion that is relative to the surface of the Earth. When we do this, we are assigning something called an inertial frame of reference. This is the object or person or location that we pretend is completely still, and we assess the motion of other objects relative to this inertial reference frame. For example, if we treat the Earth as an inertial reference frame and we ignore its rotation and movement through space, it becomes meaningful to say that this car is moving directly north at 100 km per hour relative to the ground. But if you are inside a car moving on its constant velocity, it seems as though we are not moving itself, but rather that the surroundings are moving past us at 100 kilometers per hour. The cars become the inertial reference frame that is standing still, and everything is in motion around us. It may seem strange to pretend that the car isn't moving, but remember, it's just as incorrect to pretend that the Earth isn't moving. So it really is all relative. Let's move on to the special theory of relativity, concept of ether. So what is ether? And what is its history? How did the Michelson-Morley experiment disprove the ether and help Albert Einstein develop his theory of special relativity? So let's give them a simple meaning. Ether, according to Wikipedia, in ancient medieval science, it is the fifth element or quintessence, the material that fills the region of the universe beyond the terrestrial sphere. Here are its brief history. In Homeric Greek, the word ether signifies clean or fresh air or clear sky. It was regarded in Greek mythology to be the gods' pure essence, which filled the place where they dwelt and was equivalent to the air breathed by the mortals. In traditional Greek mythology, it is also personified as Aether, the son of Erebus and Nyx. Aether is connected to the verb to incinerate, as well as the intransitive to burn or to glow. So what is Michelson-Morley experiment? The Michelson-Morley experiment was an effort to detect the luminiferous ether, a fictitious material that pervades space and is claimed to carry light waves. American physicists Albert A. Michelson and Edward W. Morley conducted the experiment between April and July 1887 at what is now Case Western Reserve University in Cleveland, Ohio, and reported that results in November of that year. How it disproved ether and helped Albert Einstein develop his theory of special relativity. In an attempt to discern relative mobility of matter through the immobile luminiferous ether, the experiment examined the speed of light in perpendicular directions, or ether wind. Michelson and Morley discovered no substantial difference in the speed of light in the direction of the movement through the supposed ether, and the speed of right angles, which was a negative conclusion. This result is widely regarded as the first strong evidence against the then dominant ether theory, as well as the start of a line of inquiry that eventually led to special relativity, which rules out a stationary ether of this experiment. Einstein wrote, "If the Michelson-Morley experiment had not brought us into serious embarrassment, no one would have regarded the relativity theory as a halfway redemption." Confused? Always remember that it's the most brilliant scientist of the 20th century, Albert Einstein, who formulated this theory. So, feel free to watch this video over and over and over again for you to understand and grasp this concept.